Hi everyone, welcome to BecodeTube. In this series, we are creating a neural network to read the MNIST database, the handwritten digits in both C++ and Python. I mean the same algorithm in C++ and the same in Python. For this video, we are gonna convert the data that we parsed in the previous video into our math library, either Numpy in Python or Eigen in C++, and we are gonna create our neural network. We are gonna do a forward propagation, the prediction, a backward propagation. We are gonna loop many times, and then when we have a good result, we are gonna test our neural network. So we want to convert this data set that we parsed, and we have the data in bytes, and we want to convert into NumPy. So let's import NumPy here. And the idea is that our data set can just return a NumPy matrix here for our train matrix. Here in our data set, then we also need to import NumPy here. And the idea is that we're gonna loop through all the images that we have, and for each image we are gonna get a list of floats, and this will become a list of lists. Then in the image class, so we are gonna get all the pixels that we have. We are gonna convert them to float, create a list of the pixels converted, and append the label, and the label will become the first column in this list. Then we have our matrix with the first column being the label. And how to check if everything is okay. So we know that the first column is our label, so the first column is going to be our y for the train set. And for the x, we are going to get all the other columns. And here we can check if our matrices are correct. We can run this. I need to put back here the correct path, because this I was working on the Windows path, right? There you go. This is a CMake configuring, but the Python we can just run. All right. So here our y for the fourth index is 9, the same as before. Our x, we have 10 items of 784 columns, and this is the, which one? The fourth one. So this array combined becomes this image here. Okay. Now let's see the C++. Let me open here, close others. Same idea. we want a function that's gonna convert from our binary data into an Eigen matrix. So we need to include Eigen into our project, but first we have to add the Eigen here, which we do all the way to the include. This was the name that I gave to the folder, and this is the path that was created when we build Eigen, and we are gonna need to pass it to our config. So it's gonna be Eigen 3 and the path. So it's gonna be this is the name that I gave again. This is the path created by Eigen. And here in the CMake, we add as a new package, and we include here. I had already prepared this, so remember to include the directory. Just put a message here, and we can see the location. Pay attention if the location is correct. So then from here, now we can include Eigen dense, and now this error here should go away. It's gonna, the IntelliSense is working. Yeah. Now we need to create this function in our dataset. Here, and we also need to include there the Eigen, and let's implement this function. So the idea here is to get the size of our image vector. We're gonna loop through all the images, and here just to store the number of pixels, it's the rows times columns, and here we are gonna create a new matrix of this size of vectors, and the number of pixels plus 1 because the label. So the same thing in the Python. The first column is going to be the label and the others are going to be pixels. So we loop through all the images, and we get the label of that image index, and we set the first column in the Eigen matrix. Then for all the pixels, we set all the other columns in that matrix for that particular image. And here we have to convert to unsigned char again. If not, we're gonna have negative numbers. But doing the unsigned char, we convert it to the correct number, and then we return the matrix. Let's check if everything is going okay here. So we take our matrix and we get the first left column, and this is going to be our Y. So our labels is the first left column, and our X is going to be all the rest of the columns going to the right, and it's -1 because we have to exclude the label, but then we get all the rightmost columns on the columns minus 1. Let's just see what is the label for the fourth index, the same as we did with the Python. Here we are gonna get the size of the x to see if it's correct. And we are gonna loop through all the columns, the number of columns, but we are gonna print only the fourth image, fourth index, right? So our CMake is already done. Let's just reconfigure it and the build. Let's go to the install directory. I have to export again because I restarted the machine. Okay. 10 items. So here the size is 10, 784. So 784 columns. So 10 images. And the index at the 4 is 9. And here are all the numbers. If we check with Python, they should match. Check this here. Yeah, they match. So we are good. Before we start the neural network, we need to make some adjustment. First, our labels, I'm gonna convert them to int. When we did the NumPy conversion here, we set everything to float, but now just the y, I want to convert them to integers. And I want to know how many categories my neural network is gonna predict. And because this case is numbers, right, 0 to 9, so I know that if I take the max y, it's gonna be 9 plus 1, so 10 categories. Probably this would be better to be as a configuration, but I didn't prepare for configuration, so I'm just taking here the max y. But if you are categorizing cars or flowers or whatever, this would be how many different flowers you have, how many different cars you have. But for the numbers, I can just take the max here. I know it's gonna be 9 plus 1, 10. For the x, we need to normalize the data, because when we are dealing with neural networks, floating precision is important. So we need to normalize everything from 0 to 1. Normalizing, we get more precision on floating numbers. And to make it easier on the calculations, we are gonna transpose our x. We transpose by a NumPy array, NumPy matrix, by just putting a t here, and we are gonna get the transposed matrix. In C++, we are gonna do almost the same thing. To get the number of categories, we get also the max coefficient. Each number in the matrix is a coefficient, so we get the maximum of those, 9. Then we do a plus 1. We get how many categories we are gonna try to predict. Again, this should probably be a configuration, how many flowers you have, how many cars you have. But for this case, I know that this number is gonna give me 9 plus 1, 10. To normalize the data, we get the X matrix and just divide by a float. This is a double, but it's going to be a floating number here. And we're also gonna have a transposed matrix to make it easier in our neural network to do calculations. And now let's start with the neural network. I'm gonna create here another folder, neural net, and here I'm gonna create neuralnet.py. And I'm importing here the numpy, and I need the number of features. So this would be the number of columns, 784, the hidden layer size, and this would be in the configuration, hidden layer size. Here I'm using 10. And the number of categories, it's also going to be 10. So this we can adjust in the config. The number of categories will depend on your case. Our case is the digits, so it will be 10 too. And here we are creating one hidden layers. So this is the weight, and this is the bias for the hidden layer, and this would be the output layer. So the weight and the bias for the output. In our main file, we add the new class that we created for the neural network. And we get the object for the neural network like this. So shape 1, as we can see here, is going to be the number of columns. So for the hidden layer size, and the number of categories. So in C++, I'm gonna have here inside the source, I'm gonna create here neural net.cpp. And here in the include, neuralnet.hpp. We guard here, and in our include, we include the Eigen. So we are gonna also have a layer, the first layer, the second layer, the weight and bias, and the implementation. Here we receive the number of features, the hidden layer from the config, and the categories will be 10. Random in C++ generates -1 to 1, numpy is 0 to 1. We need to convert here from 0.5 to 0.5 here in the C++, in the Python. I forgot to mention that we also need to offset here -0.5 for the C++, because it's already from -1 to 1, we just divide by 2. And then in our C++ file, we include our neural net. And we create our neural net object like this. We pass in the number of columns, what is the hidden layer size from the config file, and the categories from here, that will be 10. On our CMake file, I'm gonna add another library. That I'm passing in here the location for the neural net, and I need to target my executable here with the new library. I build, yeah, it builds okay, so we are good. In our neural network, let's open here Python. We want to do a forward propagation, and first we create an intermediate layer here. That's gonna be the dot product between our weight and the input. This is gonna create a matrix that's 10 by 60,000 if you put all the images here from the max items. And we add the bias into our new matrix here. Then we are gonna need a ReLU function, and a ReLU function is gonna be just the maximum between what our input and 0. So anything below 0 is gonna become 0. We only allow values that above 0. Then we pass another dot product from our output layer with this intermediate layer, and another bias we add here. And before we return this matrix, we need to do a softmax. The softmax is gonna normalize the results for each call, for each row, for each image, right? For each row represents each image. So the basic softmax is like this: we exponential the input, and we divide by the sum of the exponential. Then we return the matrix. And the idea how to use this is we are gonna loop through all the generations. This we put in the config file, and we are gonna do the forward propagation here on our transposed matrix. You see here before the transpose is 10 by 784, but after we transpose it, well, not 10, right? 10 is what we have now, and then this is gonna be 10, so it's gonna transpose here. That's why we transpose before, so we can easily manipulate here, and it will be easier to calculate this dot product. This is just for reference, right? Now let's do the same thing in C++. So in C++ here, our neural net, we are gonna need those intermediate matrix, and we are gonna need those three functions: forward propagation, softmax, and ReLU. First, in the forward propagation, we need the dot product in Numpy is easy, right? It's just a w.x. For Eigen, we use the regular multiplication. This is a regular dot product. This is the dot product for the matrix. So the dimensions need to match here. The second dimension here, the first dimension, they need to match for this multiplication to work. And in Eigen, I tried to just sum an array. Where is the? I tried. This is a matrix and this is a vector. We can't sum directly a matrix with a vector. This will be a matrix 2, right? So this is a matrix. We can't just sum a matrix with a vector. So what we need to do is, for each column in the matrix, that the intermediate matrix, for each column, we sum the bias. So the bias is gonna be applied to all the columns individually using this for loop. In this case, Python is easier. Python, you can just sum the vector. Then we need a ReLU function. And the ReLU function is a coefficient-wise maximum with 0. So the same as we did here, maximum of z or 0, so only positive numbers. In C++ is coefficient-wise max 0. So for all the numbers here, whatever is positive or 0 is gonna be returned as a new matrix. Then we do another dot product here and another bias, some bias here. For each column of the z, we sum the bias. And then we need a softmax function. The softmax function is going to be the same. We do the exponential. So we have to get the values as array and apply the exponential function. Then for the exponential function, for each column, we do the sum. Here, the sum already does that for us. Sorry. It sums by columns, each column in the resulted exponential here. And then for each column, we need to divide that particular column with the sum. So for each column in the exponential, we divide by that respective column in the sum. It's the same as here, but NumPy is wiser in the sense that it already do all this calculation by columns, while here we need to tell Eigen to do the calculation by column. It doesn't do by itself. And then in our main file, the idea is to loop through all the input generations and apply the forward propagation here. For for the CMake, we should not have any problems because our include already has the neural net and the library is still is the same. So when we build, I forgot something. Oh, here, I forgot to return. We return the last matrix here. Okay. Once the generation is calculated, we want to get the prediction. It would be something like this. But we don't want to predict every single generation, or we are gonna spend a lot of time getting predictions that are not worth. So what I do is just every fifth generation, then I get a new prediction. And let's implement this function. The prediction is just so here for each row it's gonna be an image. So then I need to get what's the index that because it's gonna return 10 values, 10 categories. So what index is the maximum value? So it's gonna return 0.02, 0. Something, etc. 10 values. And this would be the index 0 would be the number 0. It predicted that the image is a 0, or there's a 2, 3, 4. So the max value in this array, we get the argument, the index. So in this case it would be 3. So then it would return 1, because 1 is the max value for this matrix. And then this would represent that the image is, the neural network thinks that the image is a 1. That's what this says. But then we need to compare with the actual value from the label. So then we need to get what is the correct prediction here. This, I'm gonna count how many correct predictions I had. So I'm gonna compare all the predictions with all my labels. Here we do it like this. So we receive all the predictions, we receive all the labels, we compare them. If the prediction is equal to the label, it's a 1. If not, it's a 0. So when we sum, we get the total correct predictions. That will be here in this number. And then to get the accuracy, we compare the count of correct predictions with our y size. So we need to get this function here. Which is basically get the number of the correct predictions, divide by the size, and just a multiplication by 1 here, because this will be integers, and we need a float result. And here we can print some results here. Let's take a look. So only one, and the next generation only one. But I just realized that because we are dealing with random numbers, we need a seed for the random. So here in the beginning, I'm gonna give a random seed, and I need the time. Okay, we all know that the standard random is not a very good random, but for this project it's good enough. Let's run this again, just take a look. Yeah, 0. If we increase the number of generations, oh, only 10 items. Yeah, let's not save images. This is important because not it's gonna take a long time creating the image here. Let's put more image, 2000, and generations, okay, 150, it's enough. Okay, let's try here. So these numbers, they are like this, equal and low values, because we are not back propagating the information. We are not updating our neural network, so our hidden layers. So without updating this, the neural networks will just do the same calculations over and over. So we need to implement the back propagation. It's gonna be here. So the back propagation, it's each generation. We could put it here, but I like to put after the prediction. And we need this one hot y value, and I'm gonna create it before here. And let's implement these functions. First, the one hot. Basically, we create an array of zeros of this size, so for all the labels, and with 10 categories. I could pass here the number of categories, but I'm just gonna do this. I'm gonna get the max value of y and do a +1. Then we have our zeros. So on the y value, so y is the label, so if the image is a 0 or 2, but if it's a 0, then in the index 0 we are gonna add 1. If it's a 2, we're gonna put in the 2 index the value 1. So we are gonna have 10 values. Then if our index is 2, so 0, 1, 2, then here it's gonna be 1. And it's gonna do this for all the y rows, right? So y is a vector, so it's gonna be just one dimension, but for all single y values, whatever is the index, so whatever is the label, then we put a 1 here. And we return this one hot but transpose it. Also because it's gonna be easier to do calculations later. Then for our backpropagation, first we need to get the y size. I'm just saving it in a temporary value here. Here it's the derivative for the output layer, which is just the output layer minus the one hot vector. Then the derivative for the weight on the output layer, it's 1 divided by the size of the labels times this thing times the dot product of the derivative that we calculated here by the intermediate A1 here transposed. And the derivative for the bias is also the 1 divided by the size times the sum of this intermediate derivative. For the hidden layer, we are going to need a derivative ReLU function, which is very simple here. It's just if the value is greater than 0 or not. And here we are multiplying y's, the coefficient y's here, and here the transposed, and the transposed hidden output layer weight dot product with the derivative for the output. Then for the hidden layer, the derivative is 1 divided by the size multiplied with the dot product of this derivative with the passed in x transposed, and the bias is this value multiplied by the sum of this intermediate derivative. And then we can update our layers. We are gonna pass in the alpha, which is gonna control how much our network is gonna update each generation, times those derivative for each component, and we update the component. Explanations on this math here, you can check the Zhang video that I showed on my first video. On my first video, I tell you that this math is an adaptation of Zhang video, so you can take a look at that. And now we are done with the backpropagation. We can test. Now we see that we got some improvement. If we run more generations and use more items, we are gonna get better results. But for now, this is just to see if it's working or not. So to get the predictions, we are gonna need the predictions, but I don't want to calculate predictions on every single generation, so I'm just gonna wrap here only each fifth generation. I'm gonna get the prediction, and this prediction here include get predictions, the C++, where is here? For the predictions, we are gonna receive the matrix of the predictions would be this return here, and we are gonna create an output prediction here that first we are gonna zero for all the columns, and for each element we are gonna put a -1 here. Then this is gonna be an intermediate value, and for each column for the received prediction, what is the max coefficient? So this matrix, each column is gonna be an image prediction, and we are gonna have 10 rows basically, because it's the number of categories. Then for each column, so for each image, what is the max coefficient on that 10 rows? So then if the network thinks that the image is a 3, then this number is going to return 3. And then we are going to store in the output here, in the output vector. And we return the output vector. Then we need this vector here. It's gonna be outside here, the declaration of the vector. So for each prediction, we want to get how many correct ones we had based on the input labels. So to create this function, here, so we are going to receive the predictions and the labels. For each prediction, we are going to compare coefficient wise if they are equal y. So this is going to be a vector. It's going to tell us what is the predicted label, and we are going to compare if they are equal to the actual label. But this is going to return booleans. Eigen, how Eigen works. Eigen matrix, for example, what we have been using here, xf, it's because we don't know how many elements gonna be, but they are gonna be floats. There are xd for doubles and the xy for integers, but there is no booleans. So in order to mimic this behavior, there are, for example, if you already know that your matrix is 2 by 2 or 2 by x or 3 by x or 4 by x, you have these other options. If you just leave x, you don't know the size of your matrix, and that's we don't know because we know because we know the data, but if we change the data to something else, then this neural network would have to change. So I leave the x because maybe we want to change the data later in the future. But as I was mentioning, we have floats, doubles, and integers, but we don't have booleans. And a way to mimic this is to tell just get the matrix and pass in the template that we want booleans, and we don't know the dimensions. We know only for this case, but we don't know for the future. So it's a dynamic of booleans. But as we do in Python, we are gonna have to multiply this by the weights and the derivatives. So we have to convert booleans to integers, and we do that using this expression. So unary expression is gonna get element by element in this matrix, and I'm checking if the value boolean is a 1 is true, then it's a 1. If it's false, then it's a 0. So we can return now an integer vector by converting booleans to integer with this lambda expression. But we just want to know how many correct predictions, so I can just return the sum of this new vector. And then we also want to know the accuracy, and we want to print the value later. Just for now, the accuracy I'm gonna declare here outside. The correct prediction I'm gonna declare here too. So it's an integer, and this is a float. Now let's implement this function. And the accuracy is just the correct and the size. The size means the total size, right? Here how many rows we have in the labels. That's it. And again, we need a random function here. Again, random is not the best random, but for our case, it's good enough. This is to initialize our weights and bias. Let's take a look. Again, these numbers are not changing because we are not doing the backpropagation. We are not updating our neural network. So let's update the neural network now. We are going to need to one hot our labels. And we need the backpropagation. So how do we do that? First, the one hot. The one hot is gonna receive a matrix here, and it's gonna create an output matrix. First, we are gonna put all zeros, and this is the first size, so the same number of rows, and the number of columns is gonna be the max coefficient on the z plus 1. This also could be the categories if you have a different data set. But for this data set, I know that max coefficient is going to be 9 plus 1, 10. So this is going to be a matrix of this amount of rows with 10 columns. So the label, rows, and 10 columns. Then for each row, I'm gonna loop through the input labels. I'm gonna convert to integer, and this will be the index of the output. So the same as before, first we're gonna have all zeros. Then if the image is a 2, so 0, 1, 2, then here will become 1. So this is the index. In this example, it's gonna be 2. Then for that row in the column 2, I'm gonna set the value to 1 and return this matrix transposed. We transpose in Eigen, just calling the transpose function. And for the backpropagation, let me put there the header. Here the header, and I'm gonna need gradients. I have to declare here the derivatives for the gradients. And the backpropagation, first I get the size of my labels. So then for the output layer that we calculated here, I take the one hot encoded, we get the derivative. Using this derivative, I can do a multiplication with this intermediate layer, transpose it, and I divide by the size here. Then for the bias, I sum this intermediate derivative for each column, and then I divide by the size. For the next derivative, I need to create a ReLU derivative function. So let me create it here. And the derivative ReLU, again, we are gonna need a Boolean matrix. So we are using this template telling that our data is Booleans, and we don't know at this moment the size, but we are gonna take whatever we input here. For each value, we are gonna check if it's above 0 or not, and then we need this to do a C-wise product, coefficient-wise product. So for each coefficient, we are going to multiply by this result. So we need to convert from Boolean to float. So in this case here, I'm returning 1 as float or 0 as float. Here I'm converting to integer, but here I need to convert to floats. Then for this derivative, I multiply the matrix by the x transposed and divide by the size of x. And for the bias here, I sum, this is a column sum, and I divide by the size. And with that, we can update finally our neural network. So we update the weights and the bias for both layers. Considering this alpha, that is going to determine if we are updating faster or slower, and that this alpha is this input here. So with the backpropagation done, we can test it, build. So now we see that our neural network is updating. Each generation we get better results. You see that it's taking 1 minute and 9 seconds, but if we build as release, build now, release, done, 4 seconds. So by just changing from debug to release, with debug we are doing a minute, and with release 4 seconds. Now that we have our neural network working, we need to test it against the test data, because these predictions are just from the trained data. So now we need to test it against the test one. Before that, I just want to do here on the Python, because we calculate at every 5th generation, but we don't calculate the last one. So just to get the last one, we do another forward propagation to get the output. We get the predictions based on this output. We count how many correct predictions we had, and they calculate our accuracy here. Now the test. So we are gonna get what is the test image file and the test label file. We are gonna save in the same directory, and for the result, the CSV file or the image files, we are gonna save in the test folder here. First, we create our dataset. Then we read the dataset based on the max items. We check if we want to save the images in the output folder, but the CSV we always save. So the train here is gonna have lots and lots images here, but we are also gonna save the test one. We convert our dataset that's in bytes to NumPy. We get the labels from the NumPy. We get the X or the features from the rest of the columns, convert the Y to integer, normalize the features, and create a transpose matrix here. For the test, we do one forward propagation based on the transposed. Then we get a new output. Then we get the predictions based on the output. We count how many correct ones. We calculate the accuracy. And here we have our test final result. So you see our train went up to 70%, but when we get the test data set, then we go back to 64. Increasing the number of items and increasing the generations, this number should get better. Now C++. Here we do one final prediction based still on the train data. So we get the predictions. We need a forward propagation. Hold on. We need one more forward propagation. We get the predictions from that output. We calculate how many correct predictions we had. We calculate the accuracy and we print the results. Now for the test, we get what's the image file. We create our test dataset. Like here. We read based on the maximum items that we want. We check if we need to save the image or not. The CSV, in this case, I'm always saving a new result. We convert our dataset that's in bytes to Eigen. We get our Y labels from the test. We get the X features based on the right columns, -1 because 1 is the label. Here we normalize our X. We create a transposed matrix to ease our calculations. We do one forward propagation based on the X test, and we get a new output. Then we get the prediction label from the output matrix. We calculate how many predictions were correct. We calculate the accuracy, and we present the final results here. With this, we can build. No, here. Okay, our final result is around 60. Increasing the number of items and generations, we should get better results. If you liked this video, share, like, and let me know what you think.